All right, so let's take a look at this problem. Let capital F of x equal the accumulation function from 0 to x of f of t dt, where the graph of f of x, little f of x, is to the right. So we're going to go ahead and say, remember, f of x is the same as f of t. Notice how this one was using the capitalized f, which means that is the accumulation function in this case, capital F, and lowercase f is the function that we're accumulating. So think of little f of t. This will help you kind of visualize it. Think of little f of t as the rate of snow accumulation over an 8-hour period of time. So little f of t is a rate, which means if you then read the graph, at t equals 1, snow is falling at a rate of 3 inches per hour, because it's the rate of snow accumulating on the ground. At t equals 3, no snow is falling. But then at t equals 4, the snow is actually melting because it's decreasing its amount on the ground. So snow is melting at 4 inches per hour. And capital F of x, which is the area under the curve, if t is hour and f of t represents inches per hour, right? Then capital F, which is in area, is going to represent inches, also known as the accumulation of snow on the ground at any point in time x. How many inches of snow are on the ground at any point in time. So what we have here is a graph of the rate. We know that as a derivative, okay? And we're accumulating the rate. We're finding the area under the curve of the rate, which means we're actually finding, in this case, an amount. So let's complete the tables for the given times of x. I'll start it off, and then you can finish it off, and I'll give you the answers. So filling out the accumulation table, if x is 0, capital F of x is the integral from 0 to 0 of f of t dt, which is 0. And we're just doing that the same way we were doing definite integrals in the last section. If x is 1, we are drawing a trapezoid right there to get an area of 2. If x is 2, we're integrating from 0 to 2. So we're getting that trapezoid plus that rectangle to get an area of 5. And go ahead and pause the video so that you can finish that up, or the answers are 6.5 if you know how to do this, 4.5, 2.5, 3, 3.25, 3 again, and 2. Hopefully that is correct. Oh yeah, because we went down. So this will be your negative area. So now we've accumulated f of t dt. We've gathered all the areas from 0 to 0, 0 to 1, 0 to 2, 0 to 3, and so on. So we've seen that the derivative of the accumulation function is the function itself. So since capital F of x is equal to this integral, then capital F prime of x is equal to little f of x. The derivative of the accumulation function is the function itself. So can't we just say the derivative of capital F? So with that in mind, knowing that capital F prime of x, or the derivative of the accumulation function, is the function itself, let's complete the following table. F prime of x at x is 0. Well, F prime of x is f of x. Right? F prime of x, capital F prime of x, is f of x. So what we are looking at when we do f prime of 0 is we're looking at f of 0 because these mean the same thing. So f of 0 is 1. Right here. F of 1 is 3. F of 2 is 3. F of 3 is 0. So we're talking right now about the derivative of the accumulation function, which is the function itself. That's huge because the derivative of something tells us like increasing, decreasing, mins and maxes. So we're already looking at possible increasing, decreasing mins and maxes because we are already looking at the derivative of the accumulation function. So f prime of 4 is negative 4, f prime of 5 is 0, f prime of 6 is 1, f prime of 7 is negative 1, 6.5 is 0, and f prime of 8 is also negative 1. The derivative of the accumulation function is the function itself. So like I said, we can determine information for when that accumulation function, when f, capital F, increases and decreases, as well as relative extrema by looking at the derivative, which we already have in front of us. So where is f increasing and decreasing? Where does it have relative maxes and mins? Well, f prime of x, capital F prime of x, which is also little f of x, is 0 at 3, at 5, and at 6.5. That's where it's 0. Therefore, it is, if we look back at the graph, it is positive to the left of 3. See, my y values are positive up there. It's negative between 3 and 5. It's positive between 5 and 6.5. And my f prime of x, capital F prime of x, is, which is also little f of x, is negative after 6.5. So we are capital F of x, this is who we're talking about. Capital F of x is increasing from 0, because it starts at 0, is increasing from 0 to 3, and from 5 to 6.5. And capital F of x is decreasing from 3 to 5, and from 6.5 to 8. Okay, because we're only looking at, this is a rate of snow on the ground over an 8-hour period of time. So starts at 0 hours, ends at 8 hours. We have a relative maximum at 3, and at 6.5. How do I find like the y value? So my relative max is at 3 comma what, and my relative min, and my other relative max is at 6.5 comma what? Because I have maxes there because we have a 0 and it's increasing, decreasing, increasing, decreasing. What's my y value? Well, we already found the y values over here. These aren't the y values, these are the values of capital F prime. Here are my y values. So 3 comma 6.5 and 6.5 comma 3.25. Those are my maxes. And then your min is at 5, 2.5. That's your min. Okay, because it's 5 comma capital F of 5, which we found when we accumulated. This is why we spend so much time on function analysis, to really truly understand what's going on, because now guess what? If we're talking increasing, decreasing maxes and mins, we're also going to talk about the concavity of the accumulation function by looking at f double prime of x. We have capital F of x, which is the integral from 0 to x of f of t dt. We have capital F prime of x, which is little f of x. And then we have capital F double prime, or the second derivative of the accumulation function, which is the first derivative of the function itself. So let's take a look back at the curve, now that we know that, and try and ignore all this. So again, capital F double prime of x is little f prime of x. And little f prime of x is little f prime of x is greater than 0 or positive when from 0 to 1, and from 4 to 5, And continuing, 4 to 5, 5 to 6, 4 to 6. Right? And that's it. So that's where we have, that's where our graph is, that's where F double prime, I'm sorry, not F double prime, that's where F, capital F is concave up. Could they have used another letter? I hope so. But no, they did not. F prime of X is less than 0 from 2 to 4 and from 6 to 7. And that's where capital F of X is concave down. We have an inflection point. So where is F prime of X equal to 0? F prime of X is equal to 0 at 4, or F equal to 0 undefined, at 4 and at 6. And it changes signs. It changes from positive or negative to positive and positive to negative. So we have POIs, or points of inflection, at X equals 4 and X equals 6. So what I want you to do is I want you to take nicely this information. Take nicely this information and attempt to draw a sketch of the accumulation function of snow on the ground and see what you can come up with. Now, as you draw this sketch, keep in mind you already found F of 0, F of 1, capital F of 2. You have ordered pairs for capital F. You just have to apply the increasing, decreasing, the concavity, and the points of inflection. All right, so here's my graph. I do have my points of inflection at 4 and 6. I was looking back and I was saying, okay, what about the situation where the derivative of little f, which is the capital F's second derivative, what about this change right here where we go from a constant rate of change into decreasing, and we go here from a decreasing rate of change into constant? I'm going to go ahead and say that's a point of inflection as well, and it's noted in the graph. I mean, you have to do it in order to meet all the criteria. You have to switch concavity here in order to get to that point, and it matches the graph of little f prime, which is capital F double prime. So this meets all the criteria for increasing and decreasing and for concavity. All right, I know this video is a little longer than others, but it's because I spent a lot of time explaining, but I want to go ahead and do a few of these with you guys. We are doing capital F of X, the accumulation function from 0 to X of F of t dt. So we're going to find the following. We remember when we're looking at capital F only, we're plugging these X values into the upper end of the accumulation function. So the integral from 0 to 0 is equal to 0. So F of 2 is we're doing the integral from 0 to 2. And from 0 to 2, you're taking the area of a quarter of a circle. Okay, you're taking the area of a quarter of a circle with a radius of 2. So the area is going to be pi, because you're going to do pi 2 squared and divide that by 4. And then so on and so forth. You can finish all of these capital F's. You're doing the integral from 0 to 4, the integral from 0 to 6, and so on. I'll set up some of the F primes with you. Remember, for capital F prime, the derivative of the accumulation function is the function itself. So capital F prime of 4 is little f of 4, and little f of 4 is right here, and that is 0. Capital F prime of 2 is little f prime, no, I'm sorry, not little f prime of 2, little f of 2. Little f of 2, and f of 2 is 2. And you can finish the rest of those. And remember that the second derivative of capital F is the first derivative of little f. So the first derivative of this guy. And let's take a look at what's going on at 2. At 2, our derivative is 0. So our second derivative of the accumulation function is also 0. Double f prime, or second derivative of capital F at 5 is f prime, little f prime of 5. Really wish they said like A and B, so we don't have to keep saying big F, little f. Anyway, little f prime of 5. What's the slope of the tangent line here? Well, you know, it's negative. And down 1 over 1, so it's -1. And go ahead and do those right there. So in this table, on these problems, go ahead and complete the ones I did not do. And see if you can answer the rest of the questions to the best of your ability. And we will start on this page on Monday with a Q&A and work through practice problems, the homework in class together. Thank you for your patience. Thank you for watching. You guys made it, and we will come with questions ready on Monday so that we can really just nail this in the head on Monday and move on to the easy component and the kind of sum of all parts, which is the fundamental theorem of calculus. All right? Bye, everyone.